Going a little bit backwards here, but let's go back to derivatives for a moment. And we're going to try these two derivatives and see what you get when you differentiate. I think you've already seen problems like this, if not this exact problem recently. Remember that the derivative of the natural log of u with respect to x is u prime over u, right? So that means that we put the u prime, which is going to be cosine of x, over the u value, which is sine of x. And that's a pretty quick one, but notice that we've got a trig identity that tells us that that actually simplifies down to the cotangent of x. So of course, this tells us something, right? This tells us that we know that the antiderivative of the cotangent of x must be the natural log of the absolute value of the sine of x. So it's a nice one to keep in mind. And then that one's not so bad because it's a fairly straightforward quotient identity. This one is a little bit less obvious, but we'll try this. We'll do the same thing. It's still the natural log of u's that we're differentiating. So we've got u prime over u. U is the secant of x plus the tangent of x. And in the numerator, we have u prime, which is going to be the derivative of the secant of x, which is secant of x tangent of x, plus, and then the derivative of the tangent of x, which is the secant squared of x. All right, well, why is that so great? Well, turns out if we try to do a little bit of simplifying, notice that there's a factor of secant of x in the numerator that can get canceled out, or factored out. We're left with tangent of x plus secant of x as the other factor in the numerator. And you might notice that matches the denominator. So that's pretty good because that means that we can reduce to get a much more pleasing simple answer of the secant of x. So just like we saw on that first derivative, we can now undo the process, right? We now know what the antiderivative of the secant of x is. It is the natural log of the absolute value of the secant of x plus tangent of x. Kind of a weird one, but it definitely works. So yeah, these are two of the four new trig integrals that we want to try to memorize. The nice thing about this is we now can take the antiderivative of all four trig functions, right? We know that the antiderivative of the cotangent, let's use a bold black here. The antiderivative of the cotangent is the natural log of the absolute value of the secant of x, or I'm sorry, the sine of x. And based on symmetry, you might be able to guess this, but we've got a negative natural log, the absolute value of the cosine of x, when we try to take the antiderivative of the tangent of x. By the way, this negative 1 as the coefficient can, using the properties of logs, turn into the exponent for the argument. And when we raise cosine of x to the negative 1, when we take the reciprocal of this, we end up getting the reciprocal of cosine is secant. So we can actually say this is also the same thing as the positive natural log of the absolute value of the secant of x plus c. You don't need to know both of them. I think that the cosine one is probably more common, but if you like this answer better, I kind of like this answer better simply because remember, tangents and secants kind of are related to one another in derivatives and in the Pythagorean identity. So it's kind of nice to leave it like that. And also the positive tangent and negative cotangent ideas, right? So similarly, we could take the reciprocal of the argument here to get cosecant of x. And again, that is another nice way of writing that answer. Negative the natural log of the absolute value of the cosecant of x. Anyway, so we also know that the secant of x differentiates to, we just saw that, the natural log of the absolute value of the secant of x plus the tangent of x. And again, based on some symmetry, you might be able to figure out, or if you just experiment, you can find out that the cosecant is going to integrate to the natural log of the absolute value of Instead of the secant and the tangent, we're going to use the cosecant and the cotangent. So there are a lot of let me just finish. Whoops. Oh no. There are a lot of similarities and symmetries here that that you can use to help you memorize these. And again, any of these, if you're not quite sure if you're memorizing it correctly, you can always reverse the process like we did at the beginning and check with differentiation. Maybe we can try these out in some problems. Okay. So there are two ways you can think about this first example. One is just a direct U-substitution, set the denominator equal to cosine of 5x, and work it out. Another way you can do this is you can realize that sine over cosine is tangent, so this is the tangent of 5x. And we know that tangent integrates to negative natural log the absolute value of the cosine of x. So we'll just do that here. We'll have negative, well, and then we have the 1/5, right, to undo the chain rule. And we can do that. We can divide by the derivative of the argument because the derivative of the argument is the constant, right? So the negative and the coefficient are out front. Now we've got the natural log of the absolute value of the cosine of, well, the argument never changes. So if it was 5x, it's going to stay 5x. And then we'll have our plus c. All right, so a little bit of U-substitution. I didn't show the steps on the U-substitution because this is a simple one, but the U-substitution here is u equals 5x. Again, if you wanted to try u equals cosine of 5x, that would be another way of doing the problem, and I think you'll see that you'll end up in the same place. Awesome. All right. This next one, well, we can't simplify that using trig IDs, so maybe we should just try some U-substitution. Maybe we'll try the same idea of setting the denominator equal to u, which means that du dx equals, well, the 1 goes away, cosine differentiates to negative sine of x, but wait a second, the argument never changes, so that x squared stays x squared, but don't forget the chain rule. We have times 2x, and I'm out of space. Didn't leave myself much space here, so that means that dx, rather du, right? Du over negative sine of x squared times 2x is equal to dx, which is pretty nice because that sine of x squared is in the numerator, that x is in the numerator, so that's gonna have that canceling that we need to see so that we don't have any more x's in our integral and we only have the new variable u. So I'll put the x sine x squared. This is not sine squared of x, right? This is a different beast. And I'm going to put the u on the bottom, and then the dx is going to get replaced with a du over negative sine of x squared times 2x. And as we just said, the x is gone, and the sine of x squared is gone, and the negative 1 and the positive 2 in the denominator are still there. So let's remember the negative 1/2. And now we're integrating, wait a second, we're integrating 1 over u du. I think we've done that one before. I think we do this one quite a bit, right? When we do the right u-substitution, we end up getting this very simple integral that we've done a million times at this point. Of course, that's not true, not a million times, but a bunch, right? Enough times that we know that this is what it's going to integrate to. So then we just sub back, don't forget to sub back, u equals 1 plus the cosine of x squared, and that would be a nice final answer. Some people like to use properties of logs to turn this into 1 over the square root of all this. I don't like to do that, but it's certainly fine if you do. And for this last one, we'll take a look at this and we'll say, well, wait a second. If I try to let u equal the denominator, I'm going to have this extra 1 plus up here that went away when we took the derivative here, but we don't really want to put u equal to the numerator. That normally doesn't work so well. You can try it and see what happens, but I'm pretty sure you're going to hit a dead end. So don't forget that when we have a fraction with a single term in the denominator, sometimes it's very useful to rewrite this as two different fractions, right? We have 1 over the cosine of x over 2 plus sine of x over 2 over cosine of x over 2. And that should be a nice first step because we know what the reciprocal of the cosine is. It's the secant. And we know what sine over cosine is. It's tangent. And we just got done talking about how secant and tangent are both functions that we know how to integrate. So that's pretty good. That means we just, if you want to, maybe I'll go ahead and do the U-substitution here because it's a fraction and it might confuse some folks. But if we take the derivative of u with respect to x, don't use the quotient rule here. Come on, guys, we know better than that, right? This is 1/2 x, so when you differentiate that, you just get 1/2. So 2 du equals dx. So again, if you can do this sort of u substitution with a constant in your head, I'm fine with that, but I'm just going to show the steps. The secant of u, oh, my computer's doing that thing again, plus the tangent of u, and then dx is 2 du, so factor out the 2. We'll integrate the secant, and the derivative of, or the antiderivative of the secant is the natural log of the absolute value of the secant of u plus the tangent of u. And then we have a plus, and we're going to take the integral of the tangent, and we saw that that's actually going to be a negative natural log, the absolute value of the cosine of u. Cosine. So that would be the integration part, and then obviously we have the sub back in where, and I'll go ahead and distribute the 2, I guess, so I don't have parentheses. I don't know, either way. U is x over 2, and so we'll just replace every single u with an x over, whoops, with a u with an x over 2. And then plus a negative is minus natural log. Oops, I forgot the 2. I wanted to get rid of the parentheses, so then I forgot the 2. So maybe that's a bad idea, just opening yourself up to making a careless mistake. But negative 2 natural log the absolute value of the cosine of u. Or nope, lots of things floating around here, isn't there? All right, so that is a nice final answer that we can leave it. Some people will try to start combining these together using properties of logs. You're welcome to play around with that if you like. I don't know if there's much point to it, but if it makes you happy, knock yourself out.